So one, so we have now number 5 from 2025 AIME 1. So the problem says there are 8 factorial 8-digit positive integer that use 1 through 8 exactly once, and n is the number of these integer that is divisible by 22, and we want to find the difference between that n and 2025. So it's straightforward, but we have, like, even though they to provide this one, is kind of not needed, because we already know that if you are looking for the 8-digit numbers, and then they are different, so you have always 8 option for the one slot and then 7 option for the second, and it will continue all the way to 1. So there will be 8 factorial ways to get those digits, numbers. So, but we just want to know how many of those are actually divisible by 22. This is like the if you want to look for the number that's divisible by 22, that means that should be divisible by 2 and 11. So since divisible by 2 is kind of easier, so that should be even number, but 11 is just alternating sum. So for example, like if I have A, like B, C, D, E, G, H, so 1, 2, 3, 4. So I can just maybe, I don't know, like I just A, B, C, D, E. Actually, I'm going to add F as well. F, G, and H. So, for this number to be divisible by like 11, so we just need to take the alternate sum. So, which is going to be A, C, E, and G. So, let's see if this is going to help us. So, A plus C and E and G. So, whatever this sum, and then the remaining digits, so like basically B, D, F, and H. So, this difference must be multiple of 11, so I can say this is 0 mod 11. Okay. And what else do we know? We know that we are using 1 through 8 exactly once, so which means if I want to add all these digits, so A through H, so that will be 36. So A plus like B, C, D, E, F, G, and H. So this sum is 36. But now we don't really have much other than maybe using these two. So, there's 8 variable, which doesn't look fun, but if I take this entire sum, let's say this is equal to something, and then let's say this is equal to something else. So the difference between these two is going to be either 0 or multiple of 11. And we know that this guy right here is A, and then this, no, not this, that order, but so like the entire thing right here is just some of those like letters right here, and the same thing right here. So the entire thing is going to be A plus B. So now we have the difference of two things are 0 or something, and then sum is 36. So we can actually use this one to get something out of this. So let's go ahead and do that. Like if I say A plus B is like 36, and then A minus B, like A minus B could be like 0 or like 11 or 22, or I can take the negative version of these as well, but I'm gonna consider if I need to. So, and also, we have two things add up to and then two things subtracted. So, which means A plus B and A minus B should be same parity, which means if this is even, so we actually cannot have odd difference. So 11 and negative 11 or any multiple of those doesn't work. So if I start with, let's say, 0 for A minus B, and if I add this equation, you get 2A is 36, so which will force A to be 18. Okay, and then if that's 22, so you will get 50, like 58 divided by 2, which is 29. But if this is 29, that will force B to be 7, so let's keep it in mind. But at the same time, if you try to add the first 4, like the smaller 4 digit in your list, so that is actually equal to 10, right? So this is at least 10. So meaning that the B at least 10. So if that's 29, so the B will be 7, which doesn't work, and then 29 doesn't work either. So only one that actually worked is 18. So this sum and this sum should be 18 and 18. So the goal is now is to try finding some digit that is add up to 18, and whatever left will be the second pair, second quadruple, I guess. Okay, so the first thing I'll say, let's try organizing our list. So I'm going to start with 1 and 2. So that's 3 already, and then I want 18, so I need 15 more. So I can get like 7 and 8 as my first list. For corresponding list should be whatever digit left over. So that will give us like 3, 4, 5, and 6. And if I want to go with 1, 2, so maybe I can decrease this by, actually I cannot do 1, 2, I just do 1, 2. So, and then if I do 1, 3, so that's going to be 4, so I need 14 left, so which is going to be 6 and 8. So that should be fine. And if I go the remaining ones, that looks like we have 2 is missing and 5, 2, I mean 4 actually also missing. So 4 and 5 and 7. And then next one, I'll say 1, 4, that's 5, and then I need to get 18, so 13 isn't needed. So I can go with 6 and 7, and that will give us 2 is missing, 3 is missing, and 5 and 8. And like if I want to go with 1, 5, so I can probably try and see. So let's go ahead and try and see 1, 5. That is add up to 6 already. I need 12 more. But to get 12, I need like 6 and 6. That doesn't work. I can go with 5, 7, but 5 is already used. So 1, 5 doesn't really work. So the next one is 2. So let's go with 2 first, and then next smallest is 3. That is 5. And I need like 13 more. So that looks like we have 6 and 7 again. Because some was 5, some was 5, so it does kind of work anyway. And the remaining digit will be 1, 4, I guess 5 and 8. So like there is nothing else we can do. Like if you try some other ones, so you can try, but I think these are only for available cases that we have. So now we just want to kind of use this to get the total number of like digits. So like imagine like we have 8 slides, right? 1, 2, 3, 4, 5. Actually, I'm gonna use different color. So like 1, 2, 3, 4. And then let's say 1, 2, 3, 4. So look, we have 8 slides in this case. So the goal is just to finish up. So for example, if I take this guy or this guy or this guy or this guy, there is no really difference. They are kind of symmetric. So meaning that whatever works for this list, I will multiply that by 4. So I'm going to say, let's multiply that first, that 4. Okay. So that's basically of choices that we can split into 4 groups. Okay, so this group, this group, this group, or that group. That's one thing. And now we just need to decide which group, like this group or this group, will be the red ones or the purple ones. So you just have 2 choices for this. So for the like split into different groups. So which has because it does matter. And now, as soon as we decide those groups as well, we have 4 like red numbers we need to determine and to arrange those, which usually like, 4 factorial ways. But at the same time, we have to be careful. Our last digit should be even, so which means I can only choose even digits. So which is we are lucky because only half of these digit, like 2 of these 4 digit or 2 of these digit are even, so which is nicer. So we don't need any more cases. So I'll take as my last multiplication. But for the purple ones, we have no concern. Maybe I should do all that way. So 4 factorial ways to split those 4 digit between those 4 slots. And then for the last one is the red ones. I have 4 factorial ways that I can uh, place those, but I need to divide this by 2 to make sure that's even. So this is something we have. So far, we have canceled these guys. And then we have 4 times 4 factorial square. So I will just say that will be just 4 times 24, 24. And you probably remember 24 square already. So that should be like you can square, but I'm going to actually take the square of something. So like this is 24 squared, this is 2 squared, which means this is 48 squared. So if you multiply 576 by 4, you can actually do that as well. But I think I like this way because 2025 is like 45 squared because that's the year of the test. You just need to remember that. And if I take the difference between these two, so the difference of the square, that's going to be a difference will be 3, and then some will be like 93, right? So let me actually see that. So 48 square, and then let me double check. So that will be 90, 98, 103, I guess. So actually 93, not 803. Okay, so then if I multiply these, that will give us like 9 and then 729. Okay, so that was an interesting question, like divisibility by like 11 and 2 in a different way. So I think this is a cool problem. Anyway, I'll see you in the next video.